Okay, this is my second attempt to record this video. Unfortunately, I didn't have the camera focused on the bottom of the page for some of the questions, so I'm just going to go over it again. This is the physics exam for Unit 2 of Edexcel International A-Level, which was set in May 2020. Actually, it wasn't used due to COVID. They didn't use it until October. So if you're looking for the mark scheme, it sometimes gets labeled under October 2020. Okay. The first question is about wave basics. So waves can be represented on graphs. You can either have displacement against distance on the graph or displacement against time. So if you want to know frequency and period, you would use a displacement time graph. If you want to know wavelength, for example, use a displacement distance graph. It says which of the following properties can only be determined by combining information from both graphs. Well, amplitude comes from distance, the displacement distance graph. Frequency, I've already mentioned, comes from the displacement time graph, and wavelength, I've already mentioned, comes from the displacement distance graph. So the only quantity is speed, where you need information from both graphs. For example, you can get the wavelength from the distance graph, and you can get the frequency from the time graph. Combine the two and you get the speed. Alternatively, you can get the period from this and the distance from the distance time graph, which is the same in effect. Okay. Second one, two waves from the same source. So they're same source, so they're coherent, arrive at the point with a path difference of 3/8 of a wavelength. Okay. Lambda is the wavelength that tells you which of the following is the phase difference of the waves at this point. Okay, so two waves, they're out by 3/8 of a wavelength. They've given all the answers in degrees. Well, you need to know that one wavelength corresponds to 360 degrees. So 3/8 of 360 degrees is all you need to calculate. Answer is C. Question 3 is about a diffraction grating. So I'm just going to make sure you can see my calculation at the top. A diffraction grating has 300 lines per millimeter. So if you want it per millimeter, you simply have to divide the 1 millimeter by the number of slits, or the number of lines it has per millimeter. So per millimeter, it's 1/300, the separation of the slits, which is what you need for the equation. For diffraction grating is n lambda equals d sine theta, which is given here. So when laser light is directed towards the diffraction grating, a diffraction pattern is seen on the screen. The screen is 2 meters away from the diffraction grating. These are things that you need to measure. This is, I believe, core practical 6 in your required practicals, that you need to be aware of the method and what you can work it out. This normally you would get the students to work out the wavelength from the position of the first order maximum, usually on each side. So they're giving you the position of the first order maximum as 0.4 from the center. Using trigonometry, you can work out theta. Theta would be, tan theta would be 0.4/2, so 0.4 opposite over the adjacent part of the right angle triangle. So you know how to work out theta. It's using tan. Okay, so that means one of the answers must have tan in it, where theta is the correct way up. Okay, so it can only be B or D if once you know how to get theta. And then if you put the numbers in, n is equal to 1 because it's the first order maximum. That's what n means. Lambda we want to work out. D is 1/300. So there's D, and sine theta is the equation. So we're looking for sine theta at the top, 300 at the bottom. That means it has to be C or D. Can't be C, therefore it has to be D, because of what we said before. Need to be working out the angle using tan. Question 4 is about physical quantities or units. Which of the following statements about physical quantities or units is correct? Current is a derived quantity. No, current is one of the base quantities, so you just need to know that. Current is the main current base quantity. Okay, so amps is the base unit. Coulomb is a base unit. No, if current is Coulomb is based on the equation Q equals IT, so it's 1 amp times 1 second. The volt is 1 joule per Coulomb, so it's also not a base quantity, so it is not a base unit. So you only have power, which is a derived quantity. Okay, so power you could say is current times voltage, for example. Okay, or energy per unit time. So that definitely is a derived quantity. Over the page, question 5 is about ultrasound. Ultrasounds are often used for scanning. They are safe, safer than using X-rays. That's why they're used in certain situations. But this is potentially a trick question. Ultrasound has a number of different uses in medicine. It says, which of the following is the main reason why ultrasound is not used to perform scans of the chest and lungs? Well, I didn't actually know this. It's not a common question, but you can work it out even if you don't know this. So the answer is A. So you can read A in a minute, and that's the answer. But let's look at B. The duration of the pulses, that means the period of the pulses of the ultrasound, limits the amount of detail that can be seen. Yeah, well, I don't think that's applicable. Yeah, T does not affect the penetration, the period of the ultrasound. Okay. What affects the penetration is the solidity of the material, I would say. The wavelength of the ultrasound is too long. Well, ultrasound means high frequency, yeah, above 20,000 hertz. So one would assume the wavelength is not too long. If anything, it's going to be of low wavelength, okay? So I would delete B and C automatically. And ultrasound can damage the lungs. Well, we just started by saying that ultrasounds are safe alternatives to X-rays. I just want to make sure I didn't make the same mistake as before. So question 5, the answer is A. The air in the lungs causes most of the ultrasound to be reflected back. I'm not sure if you saw the bottom of question 4, because as I said in the previous video, I had to stop. I didn't zoom in to the bottom question of the page. Okay, so this is what we discussed. Current is a derived quantity. No, it's a base quantity. Voltage is a base unit. No, voltage is 1 joule per Coulomb, and so on. The Coulomb is a base unit. No, it's not. It's based on the amp. Coulombs are Q equals IT. That's where it comes from. So only B is correct. Sorry about that. Question 6. Which electrical component has the following current voltage characteristics? So current potential difference graph. At first sight, it looks like it would be a filament bulb, but it's not. Okay, it's not a diode, because diode would be only in one direction. It wouldn't be symmetrical. It only has current flowing in the positive direction. A filament lamp would actually curve the other way, so you can stop the video and look it up if you want to. But this is something that students may just automatically go for and therefore lose a mark. But once you go and do some research, you'll see that it should be bending the other way rather than the way that they've drawn it. So this is a banana skin for some students. Resistors are ohmic, therefore both in a positive and a negative direction the graph should be directly proportional. That means a straight line through the origin, so it can only be D by process of elimination. That's question 6 done. Now I'm on the wrong side. Question 7 is to do with resistivity. So a small metal cube with sides of length x. So it's a cube with sides of length x. So there we go. Is connected in a circuit. So the current will be trying to flow through the cube. Okay. The current through the cube is I, and the potential difference across the cube is V. So why are they telling us that? They want us to find out which of the following expressions, yeah, gives the resistivity of the metal. Well, you need to find the equation with resistivity in it, which is R equals rho L over A. They've given you voltage and current. Well, the ratio of voltage and current is resistance. So you replace R with V over I. V over I, therefore, will equal rho L over A, as I've written here. L is the length of the cube, which is X. The area, cross-section area of this cube is going to be X squared. So X over X squared would be, substituting for L over an A, So it'd be rho x over x squared, or the x's cancel, so it's rho over x. Change the subject of the equation to resistivity, and you'll see the answer is A. And question 8. Which of the following statements about waves is correct? Well, the answer is D. Only transverse waves can be polarized. There is no point in spending more time on this question. You want to find direct routes to the answer, and with knowledge questions, you either know them or you don't. All the others are wrong. You need to find out. If you don't understand this, go and do some revision. Okay, questions 9 and 10. I must remember to move the video up, so I'll do that now before I forget, so you can actually see both questions in the screen. Okay, 2 copper wires are placed in series in a complete circuit. The electrons in the 2 wires, so they're both made of copper, have different values of drift velocity. Well, the equation you need from the equation sheet is current is equal to N, which is the number of free electrons per meter cubed for the material. So N is constant. A depends, they haven't told us anything about A. V, they told us they have different drift velocities. That means there must be something different about them. Q is the charge of the electrons, so that's not going to be different. And because it's a series circuit, I doesn't change. So the only thing that can change is A. If V is changing, it's because A is changing. So you go straight to the answer B. Charge carrier density N is for copper, so it's a constant. Current in a series circuit, I is a constant. And length is not in the equation. There is no length, so the only variable can be is A. Question 10. Question 10 shows a potential divider. Potential divider means 2 resistors in series dividing the potential that they are given, the EMF they're given. So they're given 12 volts and they're sharing that 12 volts between them. So what do we want to know? So it includes a battery of negligible internal resistance. That means we don't have to worry about its internal resistance, although it will have some. And a light-dependent resistor, yeah. So it's showing you what's in the circuit. The potential difference across the fixed resistor, R I've called it, is measured using a voltmeter. Which of the following statements is correct about this circuit? If the resistance of the LDR halves, the voltmeter reading halves. No, because if the resistance of the LDR goes down, it will get a lower share of the voltage. So, if the resistance of the LDR goes down, yeah, the voltage of the LDR will go down. Yes, so will it halve though? So I'm just getting confused as to why I've not looked at this. The voltage of the resistor will go up, I've put. Okay, so this is question 10. Just going to see where it is. A is not the correct answer. If the resistance of the LDR halved, the voltage of the LDR would increase. Oh yes, because they're talking about the resistance of the LDR. I'm getting confused myself. Okay, apologies. So they're talking about if the resistance of the LDR halved, if this goes down, this will be a bigger ratio, so we'll get a bigger voltage. Okay, which my reasoning was correct. B, increasing the light intensity. If you increase the light intensity, more light goes in, the resistance goes down. Yeah? So the current goes up if the resistance goes down. So again, the current goes up means IR will be greater, so V across R will be greater. Increase in the light intensity, it says, would have no effect on the voltmeter reading. No, it says above. It's incorrect. The voltmeter reading added to the PD across the LDR. In other words, if you had another voltmeter here, voltage 2 across there, if you added the PD across the LDR, it would add up to 12 volts. That is correct. That is Kirchhoff's second law. The sum of the EMFs, which is 12, must be equal to the sum of the potential differences measured by the 2 voltmeters. Okay? That is question 10. Alright, so that's the multiple choice questions done. We're going to go straight into section B. Section B is about refraction. So it says a block of glass is submerged in a container of water. So this time you got water and air, water, glass going in, but we're only interested in the water glass interface. So this is what we want to look at. A ray of light traveling in the water is directed towards the glass at this angle as shown. So this angle later on they tell us is 43 degrees. They've given us the refractive indices of water and of glass. So for water is 1.33. So here is this refractive index is 1.5, and here is 1.33. Okay, so if we go to a denser material, it should bend towards the normal. So if we continued that downwards, it should bend that way. But that's not what the question is asking. Just wanted to make sure we're aware of what's happening. Okay. Calculate the angle of refraction within the glass, where the angle of reflection within the glass block when θ1 is 40. Oh, that is what they want us to work out. So they want us to work out this angle. So you have to use the two refractive indices using n1 is sine θ1 equals n2 sine θ2. This is on your equation. We know n1, so we call this one n1. We call this one n2. So n1 times sine θ1, n1 1.33 times sine of 43 must equal n2 1.52 times sine of θ2, which we don't know. Change the subject of the formula, you'll get it to be 36.6 degrees or 37 to two significant figures. Either answer would be acceptable. The next part of the question is about finding the critical angle. So that would be if we were going in the opposite direction. So this is where I was confused as to earlier. I thought they were going directly into the critical angle aspect of this. Determine the critical angle for light at a glass water boundary. In other words, going from glass into water. In other words, at what angle would you need for it to just go across the barrier, across the junction, the boundary between the two materials. So sine c of the critical angle is 1 over n, if you remember that. Well, n is the ratio of the angles in the two medium. And I made a mistake here initially, so that is where we want to go to. If we know that, sine of the two angles is the reverse of the indices, so you should have n2 over n1, okay? So we want it to be 1 over 3.85 because 1.5 over 1.33, I got it the wrong way around. When you do it the right way around, you will get a critical angle of 61 degrees. Apologies for my mistake. Please check that I've got it right and leave any comments in the if you think I've got it wrong. But I've had a look and I'm pretty sure this is the correct answer. Okay, that's question 11. Yeah, that is 61 degrees, so it should be sine of 1.33, so this one should be 1.33, and this one should be 1.52, yeah, so it's 1 over n, yeah, so that's how you get the answer to be correct, 61 degrees, okay, apologies for any confusion on that. Question 12 is then about potential dividers again. You have a 1.5 volt cell. You have two resistors both in kilo ohms, so we know the total resistance. They want you to calculate a value for the voltmeter reading. Well, the voltmeter is 55 parts out of 67 of the total voltage of the cell. So it's basically a ratio of 55 divided by the total resistance times the EMF. Okay, this is how you get the voltage value. Okay, so once you do that, you will get an answer of 1.23 volts. Okay, 1.23 volts is the answer you're looking for. And I think you just put it to 2 decimal places, or you could just put it to 1 decimal place. It's fine, because they've only given it to 1 decimal place here. The student then sets up a circuit and observes that the reading on the voltmeter is actually lower than the calculated value that we just made. Explain 2 reasons for the lower voltmeter reading. Well, the main reason I would put is all cells have some internal resistance. Okay, so if that happens, the EMF will be actually, when you're actually drawing a current, when you draw a current, the current goes through all of the circuit, including the cell itself, and some of the EMF voltage is lost volts. Yeah, because the current going through multiplied by the internal resistance will be equal to the lost volts. Okay, so you will actually have slightly different, slightly lower 1.5. So when you do this calculation here, the EMF will be lower than the 1.5 that's shown on the cells. That's the main explanation. Other possible reasons that they were accepting, you could say there will be some resistance in wires and connections. So this is, I think, just becoming a little bit too generous with the mark scheme, but that's what the examiners have got. So I'll let you read those as an alternative answer, because technically it's correct, but I think they will be insignificant. The main one will be the one I told you about, which is the internal resistance. And voltmeters in parallel, it says, will affect it. Well, actually, voltmeters, if they're good, have millions of ohms, so they don't. I don't think that will be a significant effect, but technically they are correct. So you have to allow students to get those alternative marks. So again, have a look at the mark scheme if you want to see their wording of it. Okay, question 13 is about sound cancellation. They called it active noise reduction, or ANR, a system used to reduce unwanted noise. So this will be destructive interference. In ANR, a second wave is produced that cancelled the first. So if you got like engine noise in a, you can get rid of it by producing the anti-noise to the engine. ANR is used in aircraft to reduce the noise heard from the engine. So usually on business class or first class, they give you headphones and it's got that built in, and it can just get rid of the background noise when you're listening to something. On a particular flight, the noise from the engine has a frequency of 0.85 kilohertz, so it told us what it is. The graph shows a possible second wave to be used as the ANR. Okay, so given you a graph of displacement against distance, you can work out the wavelength is 0.4 from this graph. And they want you to determine whether this would be suitable to cancel the noise from the engine. Well, if it's able to cancel it, you want it to be the same frequency. So let's see. They've told us that the speed of sound in air is 340. We know the wavelength is 0.4. Well, it gives us an answer of 850 hertz, which is 0.85 kilohertz. So this would be the same frequency as the engine noise. Okay. So it would be a suitable frequency to use for destructive interference. That's question 13 done. Part A. Part B. So for a passenger in an aircraft, the noise from the engine travels as a wave towards the passenger from the front. So the engine noise comes from the front because he's facing the front of the aircraft. An ANR system creates a second sound wave that is directed towards the passenger from the side. So is this a good idea to do it from the side? As shown. So if it's coming from here, engine noise is going from there. Are they going to create an effective destructive interference system? Explain how this can lead to the sound being cancelled for one ear but louder for the other ear. This is a 6-mark question, which means based on the quality of your written communication, and this highlighted by the asterisk in the question. So this is a communication question. What I wrote is sound from the ANR has to diffract to reach the furthest ear. So if it's coming from the left, it has to go round the head as the obstacle and diffract round it. Okay? Sound gets cancelled where or when destructive interference occurs. So you get a mark just for knowing what destructive interference means. Sound will get louder, however, where or when constructive interference occurs. So that's 3 easy marks just for communicating that you know what destructive and constructive interference means. So if sound gets cancelled, destructive interference, where the waves, it is due to the waves being in antiphase. So now they want you to, as well as saying destructive interference, they want you to correlate that and explain that you know it's to do with the waves being in antiphase. Okay, so one wave will come like that, and the second wave will be in opposition to that. So one peak arrives with a trough, and alternatively the other way around. When they both arrive, the peaks arrive together, they're in phase, you will get constructive interference. So that's automatically 5 marks. And finally, I have my first point where it says sound waves have to diffract to get to the ear on the side. It has to diffract around it. So if the distance between the two ears is equal to half a wavelength, yeah, which is 20 centimeters from the question that we had in part A, the wavelength we knew was 40 centimeters. One ear will receive sounds in phase, while the other will receive the sound half a wavelength later, and therefore it will be in antiphase. So one will be louder and one will be quieter. So that's, I think, the only way you can get clarity in this answer. Okay, hope that makes sense. So they give you marks based on the clarity and the logical reasoning and the correct use of terminology. Okay, again, have a look at the mark scheme, but I think this would give you the full marks. Okay, question 14 is about the photoelectric effect and the work functions. So it has the work functions of 4 metals in this table, so 4 different metals. Now, for those of you who haven't studied the photoelectric effect or haven't revised it, you need to remember that each metal has a minimum energy required to allow an electron to escape its surface. Okay, and obviously the electrons closer to the surface will escape more easily than electrons deep inside the material. So the minimum energy required is called the work function, as measured in joules. So what is meant by the work function? The work function is the minimum energy required to release an electron, otherwise also known as a photoelectron, from the surface of a metal. Okay, so that as long as you know it's the minimum energy required, you'll get the mark for understanding the work function. Okay, the equation for the photon energy coming in, overcoming the work function, phi is the symbol for work function there. So the energy comes in as a photon, Planck's constant times the frequency of the photon, uses some of the energy to get the electron to the surface, and any spare energy, in other words the difference between these two, will become kinetic energy of the released electron. Okay, what's it going to ask us? When light has a frequency of 6.32 times 10 to the 15 hertz and is incident on a metal, the photoelectrons are released and they have a maximum kinetic energy of 3.6 times 10 to the minus 18 joules. Okay, so now that means that will be the maximum kinetic energy. That's what they're saying. So we know that the maximum kinetic energy is this part of the equation, and we know that it could be one of these 4 metals, and we know that the frequency is that, and h. So first of all, you need to know that the photon energy is hf. The equation is given to you on your equation sheet. Multiply, there is h, multiplied by the frequency you're given from the question, and you get this much. The photon energy will be 4.19 times 10 to the minus 18 joules. Okay. So once you know that, you know that the work function will be this minus the maximum kinetic energy. So you take away this value from this value, 4.19 times 10 to the minus 18, minus 3.6, the maximum kinetic energy gained by them, and that difference will be the work function. You see you get a value of 5.9 times 10 to the minus 19. Well, that is very close to magnesium, so this must correspond to magnesium's work function. Okay? Okay, so that's the first part of question 14. The second part of question 14 is now about ultraviolet radiation. So now if we have ultraviolet radiation incident on a potassium plate, yeah, if the radiation behaved as a wave, there would be a time delay before the electrons were emitted from the plate. Well, why would that be? Because to absorb enough energy, it would take enough time if they're coming in as a wave. The idea about a photon is different. The photon is releasing all its energy to the electron in one go. So calculate time taken for a potassium atom to absorb enough energy, if it was a wave, to release an electron. Okay? So we know the work function for potassium given in the table, yeah, if I just bring that back, you can see is 3.62 times 10 to the minus 19 joules. So that's the minimum energy required to absorb enough energy. That's the minimum amount of energy required, okay, to release an electron. And then it probably won't get released, but that's the minimum amount of energy required. They've told us that the intensity of the ultraviolet radiation is 38 milliwatts per square meter. Yeah. Now intensity is the power, watts, divided by the area. So you could say the power is the intensity times the cross-sectional area. The area over which a potassium atom absorbs the energy is 8.1 times 10 to the minus 20 meters squared. So they've given us the area. So that allows us to work out the power that it will absorb. Yeah? And that would give you a value of 3.08 times 10 to the minus 21 watts. Well, that's not, so that's 3.08 times 10 to the minus joules per second. Well, to build up this much joules, you have to multiply this power by the correct time. Or to work out the time required, you divide the energy by the power. Okay? Because power is equal to energy over time. So if we want time, the energy is phi divided by the power, so that's just algebra. And if you see, it would take 118 seconds if it was behaving like a wave. But photons are not time dependent in that respect. Okay, so that's evidence that light behaves as a particle, the photoelectric effect. In practice, electrons are emitted from the plate as soon as the ultraviolet radiation is instant on the plate. Explain how this provides evidence for the particle nature of electromagnetic radiation. So the way I've answered it, each photon or packet of energy is E, which equals HF. It releases one electron. So each photon releases one electron. So one photon, one electron. Photons are packets of energy. They release all their energy. I changed it, all the energy, I changed to all their energy to one electron. So I think that will give you the full marks. Hope that makes sense. Okay, the next question is the Bohr model of the atom. Okay, question 15. Niels Bohr developed an early model of the atom where electrons could only exist in fixed orbits around a nucleus. So we know that already from our studies in GCSE. When an atom is ionized, an electron moves from its orbit around the nucleus to be free from the atom. Yeah, free of the atom. Bohr derived an expression for the ionization energy in joules for a hydrogen atom. So the energy required, ionization energy required, is E squared over kh, where these are all constants. E is the charge of an electron from the datasheet provided. K is given to you because you don't normally meet K until year 13. It's actually called the Boltzmann constant. So don't worry about it. It's a value. It's actually not the Boltzmann constant. It's the value to do with how much charge you need per volts per meter. Okay, coulombs per charge per volt per meter. So this is done when we do capacitance and electric fields. So they've given you the values because it's just a number that you need to plug in there. And h is Planck's constant. And m is the mass of the electron. And obviously 8 is the number. Okay, so they want you to just plug in those numbers to calculate the energy required for a hydrogen atom in electron volts. So you just, E is 1.6 times 10 to the minus 19. You square it. And then you divide it by 8.85, the value given, times 10 to the minus 12, K. And you multiply that by h, Planck's constant. So these are where the numbers come in. It's basically number crunching. Don't forget, you have to square the whole thing. So if you put it in exactly, as shown in the equation. You put the values in. 9.11 times 10 to the minus 31 is the mass of an electron, and you divide that by 8. This is what Planck said. You come up with an answer of 2.17 times 10 to the minus 18 joules. Now, to convert to electron volts from joules, you simply have to divide by 1.6 times 10 to the minus 19 electrons. Okay? Now, for those of you who want to know, energy is always equal to charge times voltage. Okay? Because that's the definition of volt, is energy per unit charge. So if you want to work out an energy in joules, and you know the charge is 1.6 times 10 to the minus 19 for electron, you multiply it. So we know this is an E. We want to know what is the voltage required, and that would give you a value. So if you want to work out how many electron volts it would be if you give 13.6 volts to an electron, that's how much energy it will gain in joules. Okay, so that's the first part of question 15. Part B, the Bohr model, it says, can be used to predict an approximate radius for an atom. They're giving you another equation. So again, it's number crunching. The equation for this radius of the hydrogen atom is R equals h squared k over pi divided by m divided by e squared. Again, these are all numbers. Okay, these are all as in part A, and pi is obviously 3.141, etc. So all this data is provided to you. A student suggests that for a speed of 1.4 times 10 to the 7 meters per second, neutrons would have a wavelength similar to the radius of a hydrogen atom. So the student's suggesting something else. So what have you got to do? You've got to determine whether the student's correct. So he's saying neutrons would have a similar, would have a wavelength similar to the value calculated for R for the hydrogen atom. So they want you to compare the R value that you get for the hydrogen atom with the wavelength you get for the neutron. Neutrons. So we need to know how to do that. Well, the wavelength for a neutron is lambda for a neutron is the Planck's constant divided by the momentum of the neutron. The mass of the neutron is 1.67 times 10 to the minus 27, which is given to you here. And the velocity that the student has suggested is 1.4 times 10 to the 7 meters per second. So there's the momentum and Planck's constant on top. That gives you a wavelength of approximately 2.84 times 10 to the minus 14 meters. So that's one of the values you need to calculate. Second one is, can you calculate the radius for a hydrogen nucleus using the values given? Again, it's number crunching. I'll let you go through it this time on your own. H squared, K, same K they gave you before, pi, constant, mass of the electron, and again divided by the electron charge squared. When you put all the numbers in, if you do the calculation correctly, it comes to 5.3 times 10 to the minus 11. Well, you can see this is 10 to the minus 14, this is 10 to the minus 11. They are not lambda. The wavelength for the neutron is much smaller than the hydrogen radius. Okay, so the student is incorrect. So I put lambda n is much smaller than the radius for hydrogen, and that takes us to the end of question 15. I'm going to stop the video now, and I'll do the last part of the exam in a separate video. Okay, so remember to like and share the video for any students you know who are doing the same paper as you, and also subscribe if you want to know where part 2 of the answer to this exam is going to be ready. Okay, thank you very much for watching.